It's a tremendous honor to be standing in front of you and reflecting upon Stuart and everything that he did, everything that he imparted to many of us, and of course, as I reflect for myself, things that I learned from Stuart. I want to thank the organizing committee, Joyce and Paul, and before I forget, Brian Fujikawa, who obviously did a tremendous amount of work here, herding everything together. So once again, Brian is making everything work really well. He did that in this experiment too. So yes, I credit Stuart with putting me up in front of the department for a colloquium a few years ago. And it's really indicative of his style. He was not interested in taking credit for things. He was much more interested in challenging, pushing the limits, experimental limits, sometimes personal limits. And I was reflecting on some of the remarks that we already heard this morning as I was doing final touches on a talk. It seems like that's not a lost art in physics. Talking about teasing his friends. Well, you know, after I did this work as an undergraduate, there really wasn't much to say about me, right? So he would introduce me to people at conferences. Meet Justin Mortara. He's famous for being well known. And I didn't escape that tagline for any number of years. The other thing I remember about Stuart is he was so rounded out, if you will. He had interests in a lot of different areas, and he had an eye for things. And one of the first times I visited his office at this time was Argonne National Laboratory, I was impressed by his choice of office decor. Some of you may not know what this is. If you visited his offices, you would have seen the Garden of Earthly Delights, work by Hieronymus Bosch. This is a triptych that actually hangs in a church, Catholic church in Spain. Stuart asked me upon looking at it to take a closer look. And you see all sorts of things going on in here, things that you wouldn't necessarily expect to see hanging up in a church, some daggers, some fornication, some various other things. And it made me think about Stuart and how he always wanted to, you know, be a little bit of that nudge, a little bit of, hey, take a close look at this. It's not necessarily all as it appears. We also heard a lot of references, and I think in part because Brian sent out a message where we had this wonderful link to this YouTube presentation from the Luis Alvarez Symposium, where we got to hear Stuart, and I hadn't heard Stuart speak in years, and it just brought me back listening to that clip. And I zeroed in on something that he had taught me time and time again, and this is a distillation of it. I have to read it. It is possible for experimentalists with all good intentions to sometimes delude themselves into believing a result they might like is the result of the experiment. This is true in physics. In the world I am today, in medicine, it is doubly so true. But now we're going to talk about the 17 keV neutrino, and I'll reflect on a comment of Roger's. I think this is the only talk I can give in Berkeley. I gave it in the colloquium some odd years ago. Now I'm back giving it the same talk again. Unfortunately, that talk was on transparencies, so I had to do a little scanning and transposition, but that tells you the approximate error of the talk. I'm going to mention a little bit about the history of that neutrino, enter Stuart, the spectrometer, and some inexperienced undergraduate, and then back to that wisdom and how it's being applied beyond physics. So regarding the nuclear beta decay and the 17 keV neutrino, this particle was first discovered looking at the beta decay of tritium, subsequently other beta decays. Beta decay is a continuous spectrum, and if there is a neutrino mass, it appears here, and this is an expression where one assumes that there's a zero mass neutrino mixing with a non-zero mass neutrino. And the 17 keV neutrino was first discovered, reported by Simpson in 1985. 17 keV neutrino causes a distortion, or kink, at the end of the continuous beta spectrum. Here, this is illustrated. This is for sulfur-35 beta decay, and that kink is visible because that's at 20%. And this distortion was hypothesized to be solved or explained by the existence of a 17 keV neutrino. Well, now we've got some further evidence, what I would call kinky evidence for the 17 keV neutrino. And these plots were all over the place at the time. Here's a kink, and there's a kink, and there's another kink, and we talked about how kinky it was back in those days. And this was the work of Hyman Jelly, who also saw a heavy neutrino and some other beta decays. Their work indicated that there was a 17 keV neutrino at a 1% mixing level. There were additional positive results also reported. This was a challenge to the standard model. And although I didn't follow very many of them at the time, I will confess, it certainly kept many a theorist churning out seminar talks about how it might be accommodated. So it was a great debate. It was an unresolved question because there were these positive results. They were only reported in solid-state detectors. So was it some solid-state effect? There was some speculation, some residual effect in these detectors. There were also some significant negative results. They were done with largely magnetic spectrometers, and the critique of those experiments was that, well, there was an instrumental correction factor, and maybe that was somehow hiding the neutrino. And the very first time I ever came to Berkeley, I found these proceedings in my old files, was the workshop on the 17 keV neutrino question, which was held here in December of 1991. But going back to Chicago, where I first met Stuart, I was sitting in his class, Physics 237, Nuclear Elementary Particle Physics, in the spring of '91. And you know, it's amazing what you keep and what you throw away, but thank goodness I kept some of this stuff, right? So here it was, some April day, and Stuart's teaching us about the 17 keV neutrino. And I don't know how many of you have had this experience. I hope many of you had, where you're in a class and you're learning something for the first time, and you get so excited about it that you're trying to keep up with the notes, and your mind is racing one step ahead of where you think it's all going, and the notes end up to be absolute garbage. But you remember that feeling of being excited about what was being presented. And at the end of the notes, which were largely between this part where I'm just drawing beta decay, between here and at the end where this is supposed to say would yield a kink, it's absolutely unintelligible. But I remember being really, really excited. And I remember at the end of this lecture going up to Stuart and saying, this is really neat. I mean, could you do an experiment like this? Could you do an experiment like that? He instantly detected this enthusiasm. And one of the things Stuart was very good at doing is tapping into energy and channeling it. He said, well, you know, if you're really interested in this, why don't you come out to Argonne? We've got an experiment we're thinking about putting together. Little did I know. So here I am. Thanks for recovering this picture, Brian, of a younger me filling some liquid nitrogen, it appears, into this spectrometer at the physics division in Argonne. And this, one thing that hasn't yet been said about Stuart, and I want to make sure that it's remembered, Stuart was very, very resourceful. Others might say he was cheap. But he was very resourceful, and this spectrometer, we didn't build this spectrometer. This spectrometer just happened to be there. Stuart had a remarkable, at least at Argonne and I'm sure elsewhere, a remarkable equipment inventory in his mind of things that were all over the place. And he knew about this spectrometer and how it might be particularly useful for a 17 keV neutrino experiment. I will also go on to say that part of my introduction to the physics division at Argonne was Stuart would tour me around where various pools of equipment were kept. He didn't necessarily say I should use some of that equipment, but he did show me where it was. So here was the spectrometer that we used. It was a superconducting solenoid field in this direction that would transport beta or electrons from the source to a silicon lithium detector. And this was great because it gave us a very large acceptance angle. We took essentially half the solid angle of the emitted particles. And the solenoid was configured such that the field strength was highest at the source and lower at the detector. So these confined electrons would go towards the detector and actually get naturally collimated by the magnetic mirror effect, or rather, as if they scattered back, they'd be reflected back into the detector, and the energy would be summed, so that the response function, as we talked about it, of the detector would be more symmetric, have less of a backscattered tail to it. And this turned out to be a very important element of the experiment. So lots of data collected, some trials and tribulations, of course, lots of learning along the way, invaluable things. But we went very fast, and we were fortunate enough to arrive at some very nice results. Here on the left was the actual measurement of the beta spectrum, that continuous spectrum where we were looking for that kinkiness. And over here on the right, extruded from the paper, was our result. And if there had been a 17 keV neutrino, it would have followed that Kinky curve. It actually had better agreement with the non-Kinky curve. So we go back and we say, well, that was good, and that was really the substance of my undergraduate thesis, but Stuart wasn't content. And I use these words again. Did we just get the result that we might like, or did we get the result of the experiment? So did we get it right? Did we get it right? Well, so not only were we going to work out and report the non-finding of the 17 keV neutrino in the beta decay of sulfur-35, but we were going to then, and we did, create a special source, which was a combination of two beta emitters, sulfur-35 with an endpoint of 167 keV, and carbon-14, which has an endpoint of 156 keV. These two sources mixed together, carbon-14 in a much smaller amount, order of 1%, produces a distortion, right at about 156 keV or about 11 keV below the endpoint of sulfur-35. And we should be able to see that if we're doing things correctly. And in fact, that's what this plot is. It wasn't quite as kinky, it's a little smoother, but the fact is that we did see this effect. So we measured nothing, but we wanted to prove that we'd gotten it right. We submitted the paper. Did we get it right? And I actually dug this up. I would say, yes, we did. It took a little while to make its way through the refereeing process, but to Stuart's credit, this is what the referee had to say. It is probably the most definitive work on the problem of the 17 keV neutrino that has been done. In my opinion, it is an excellent piece of work. Without much doubt lays to rest whether there is such a particle as a 17 keV neutrino. It was really heady times. It was an absolute joy to be working with Stuart at that time. I was always amazed that whenever I had the opportunity to do something and I showed an inclination to do it, he just got out of the way. He was so encouraging, so enabling for myself as a young student. And it was really an absolutely tremendous experience, and I've learned a tremendous amount from him that I take forward to this day. I've learned perhaps to be resourceful, to know where things are, but also if you've got somebody that's got a lot of enthusiasm, a lot of energy, get out of the way and see what they can do. And with his guidance, we did some very, very good things. So I do want to also take a moment of time to tell you how Stuart's had an impact beyond physics. As I left the world of physics and went into the medical devices, his words and his thoughts and the way he approached problems came with me. And in particular, I want to share with you something that impacts all of us in this room. And it has to do with drugs, pharmaceuticals. On the right, you can see here various little things. FDA warns about QT studies. FDA rejects drugs. Certain antidepressants may prolong QT. Azithromycin, that's a Z-Pak, by the way, poses risk of potentially fatal arrhythmias. This is the world that I spend a significant amount of time in these days, and it has to do with the prolongation of something called the QT interval, which is measured on an electrocardiogram. This is the electrocardiogram. And for those of you, most of you have probably seen that before, but you know, this is good, beep, beep, beep. This is bad, right? Okay, that's all you need to know about the electrocardiogram. Okay, so, but in this world, we measure this thing called the QT interval between this point there, excuse my shake, and that point there, the end of the T wave. And we measure that because it's a prognosticator for a potentially fatal arrhythmia called torsade de Pointes. So new drugs, as they're developed, are always tested to measure to see if they do prolong this interval. But you know what? This is kind of a measuring nothing and getting it right challenge. Because unfortunately, drug developers are looking to exclude a very small variation. We're not talking about doubling this interval. We're talking about increasing it by 5 milliseconds. And for reference, up here, that one little box is 40 milliseconds. And these aren't particles, these are hearts. They are not subject to the same sort of normal distribution and behavior. There's a lot of noise in these experiments. There's a lot of biological variation. There's a lot of underlying things that make this very difficult to measure. But they want to exclude it to about a 5 millisecond effect. So it's a tough experiment to do, and suppose one measures 0, did you get it right? Now remember, we talked about the experimenter, do they get the result they like or the result of the experiment? Well, of course, in drug development, when you don't want to see anything, it's kind of important that you don't get biased by that. So there's a lot of discussion about how to handle that. And I, by no means, have been the only voice in this, but I was one voice, and I think I can safely say I was the only voice from the physics community, or having been from the physics community, that said, you can't do these experiments unless you have a way of, in essence, proving what we call in this world your assay sensitivity. Can you actually detect such a small effect if it was there? And so guess what? I used in this case, the stories of heavy neutrinos and how that was an unresolved question until somebody proved first they didn't see it and they would have seen something if it was there. And well, just like the heavy neutrino search, guess what? In this drug development today, we use something called a positive control. We actually take, in the world of drug development, we refer to patients as subjects, provide subjects with moxifloxacin, which is an antibiotic which we actually know prolongs the QT interval by a small amount, 5 to 10 milliseconds. You blind the analysis, and you see if you see it. And believe it or not, sometimes people don't see it. But you should see it if you have a properly designed experiment. And if you see the MOXIE effect and you see no effect on your primary compound, then you've probably gotten it right. Here's the MOXIE effect. And it is a wonderful reminder of how these basic lessons in physics have applicability in fields far beyond. And I'm going to say thank you on that. Thank you to Stuart for teaching me these things. And thank you all very much for being part of that education that I now use in the world of medicine. Thank you very much.